Right now, you are hurtling through an ocean of darkness at speeds that would disintegrate steel. You orbit a monster you cannot see, trapped in a spiral you cannot photograph, racing through space on a rock so small that the entire history of human civilization could vanish tomorrow and the galaxy would never notice. We will cross distances that shatter comprehension, visit structures that dwarf imagination, and confront a truth that makes every human achievement seem like a whisper in an infinite void. Before we're done, like and subscribe if you're ready to feel impossibly small. Let's begin. A light year is the distance light travels in 1 year. Light moves faster than anything in the universe. It crosses the space between Earth and our closest star in just over 8 minutes. Yet even at this impossible speed, light takes an entire year to cover what we call a light year. Here's what that means in miles. Take the number 5.8, add 12 zeros after it. That's roughly 5.8 trillion miles. Your car would need to drive continuously, never stopping for fuel, never pausing for rest, for more than 6 million years to cross this distance. No engine exists that could survive even a fraction of this journey. Scientists measure space using light years because normal units break down completely. Miles and kilometers become useless. Saying something is 17 trillion miles away tells your brain nothing. The number is too large. It has no weight. But saying something is 3 light years away gives us a framework. We can imagine light, that fastest thing, racing through darkness for 3 full years before arriving. Even our nearest neighboring star system sits more than 4 light years distant. The light you see from it tonight left that star when you were 4 years younger. If that star exploded right now, you wouldn't know for 4 more years. The distance acts as a time machine, showing us not what is, but what was. Everything in the galaxy is measured in these units. Our star orbits the galactic center at a distance of roughly 26,000 light-years. The galaxy itself stretches 100,000 light-years from edge to edge. These numbers should terrify you. They should make you feel untethered from reality. Because here's what comes next. A light-year is the smallest unit we'll use in this journey. Everything that follows makes this distance look trivial. The structures we're about to explore are so vast that even light years start to feel inadequate. What you think is far is only the beginning. You live in a specific place within the Milky Way, not randomly scattered, not floating aimlessly. You occupy an exact location that astronomers have mapped and confirmed. That location is the Orion Arm, sometimes called the Orion Spur, a minor spiral arm that connects 2 larger structures. The galaxy has several major spiral arms. The Perseus arm lies farther from the center than we do. The Sagittarius arm curves inward toward the core. We sit in a diagonal bridge between these giants, a smaller feature that astronomers debated about for decades. Some called it a spur, others insisted it qualified as a full arm. Recent observations have settled the argument. It's substantial enough to matter. You are not in the middle of this arm. You're not at its edge either. You sit closer to the inner boundary, the part that faces the galactic center. This placement matters more than you might think. Location determines what you see in the night sky. It determines your safety. It determines whether the radiation from the core reaches you. The distance from our position to the galactic center has been measured with increasing precision over decades. The current confirmed estimate places us roughly 26,000 light-years out. Some measurements suggest 27,000. The uncertainty comes from the difficulty of measuring distances across such enormous spans while trapped inside the very structure we're trying to map. Think of it like trying to measure the size of a forest while standing in the middle of it. You can see individual trees. You can walk between them, but determining where the forest ends? That requires different methods. For the galaxy, astronomers use stellar clusters, gas clouds, and the motions of stars to build a map. Each technique refines the picture. Our position is not at the center. It's not at the edge. It's roughly halfway between. If the galaxy were a vinyl record, we'd be about midway between the label and the rim. This halfway position means we're far enough from the core to avoid its violence, but close enough to benefit from the rich stellar population around us. The plane of our solar system doesn't align with the galactic plane either. We're tilted at an angle of about 60 degrees. It's almost like sailing through the galaxy sideways. This tilt means that when you look at the band of the Milky Way stretching across the night sky, you're looking at the edge-on view of our galactic disk from a diagonal perspective. Above the galactic plane or below it, we sit slightly above by about 55 light-years. That's barely anything on galactic scales. We're practically riding along the equator of the galaxy's disk. This proximity to the mid-plane keeps us embedded in the thickest concentration of stars and dust. But there's something stranger about this location that nobody talks about. The Milky Way looks like a disk. Everyone knows this. But what they don't tell you is how shockingly flat that disk actually is. The galaxy stretches 100,000 light-years across. Yet the disk, where most stars live, measures only 1,000 light-years thick at the spiral arms. Take a sheet of paper. The ratio of its width to its thickness is roughly the same as the galaxy's. You're living inside cosmic origami. This flatness is not a gentle curve. It's an extreme compression of billions of stars into a thin plane. Why does it form this shape? Rotation. The entire galaxy spins. As it spins, gravity pulls everything toward a common plane, while angular momentum prevents total collapse. Stars, gas, and dust settle into the thinnest possible configuration that still maintains structural integrity. Think of it like pizza dough spinning in the air. Centrifugal forces stretch it flat. The central bulge at the galaxy's core breaks this pattern. There, stars cluster in a sphere roughly 10,000 light-years in diameter. But outside the bulge, the disk dominates. Most of the galaxy's visible matter concentrates in this paper-thin structure. Our position just above the galactic plane by 55 light-years means we sit almost exactly on the equator. Any closer, and we'd be submerged in the densest concentration of interstellar dust. That dust blocks visible light. It would obscure our view of distant stars and make astronomy nearly impossible from our vantage point. The thin disk contains the youngest stars, newborn from collapsing gas clouds. The thick disk, slightly puffier, at around 2,000 light-years in some regions, holds older stars that have been kicked out of the thin disk by gravitational encounters. But even this thick disk remains shockingly compressed compared to the galaxy's overall width. If you could somehow stand outside the galaxy and look at it edge-on, you'd see a glowing line stretching across space. The central bulge would appear as a bright bulge in the middle. The disk would taper to almost nothing at the edges. From that perspective, the Milky Way looks more like a cosmic razor blade than a majestic spiral. This flatness creates a strange optical effect. When you look at the Milky Way band arcing across the night sky, you're seeing the combined light of billions of stars compressed into that thin disk. You're looking through the disk from inside it. The densest concentrations of stars lie along that band because that's where the plane cuts through your field of view. But this flatness also means something else, something most people don't realize. You are moving faster than a speeding bullet right now. Much faster. You're moving faster than any rocket humanity has ever built. You just can't feel it. The entire solar system, everything from our star to the farthest icy bodies at the edge, races around the galactic center at more than 500,000 miles per hour. That speed is confirmed through decades of astronomical measurements. Scientists track the motion of stars, measure the Doppler shift in their light, and calculate orbital velocities. The numbers don't lie. We're hauling through space at velocities that would vaporize any spacecraft we could build. Why don't you feel it? Same reason you don't feel Earth's rotation. You're moving with it. Everything around you shares the same velocity. The air, the ground, the buildings, the clouds overhead, all of it moves together in a synchronized rush around the galactic core. There's no wind resistance in space, no friction, No sensation of movement. But here's where it gets strange. Despite moving at over 500,000 miles per hour, completing one orbit still takes an incomprehensibly long time. The distance around the galactic center is so vast that speed becomes almost meaningless. It's like trying to sprint around the Earth's equator. Even if you could run at highway speeds, the sheer distance would take forever to cross. Stars closer to the galactic center move faster than we do. Stars farther out move slower. This creates a spiral pattern that rotates like a pinwheel. But individual stars don't maintain their positions in the spiral arms. The arms themselves are not fixed structures of stars. They're density waves, regions where stars temporarily cluster as they pass through, like cars bunching up in traffic. The speed we're moving at is determined by the mass inside our orbit. All the stars, gas, dust, and mysterious dark matter between us and the center contribute gravitational pull. That pull accelerates us. It keeps us from flying off into intergalactic space. It's a delicate balance between inward gravity and outward momentum. If we moved slower, we'd spiral inward toward the core. If we moved faster, we'd escape the galaxy entirely. Our current speed represents an equilibrium, a cosmic balance that's been maintained for billions of years. The solar system has made roughly 20 orbits since it formed, 20 laps around a track so large that each lap takes eons. Other galaxies move even faster. The Andromeda Galaxy rushes toward us at more than 200,000 miles per hour. When it arrives, the collision will reshape both galaxies into something new, but that's still billions of years away. Right now, you're focused on a more immediate question. How long does one orbit take? The last time Earth occupied this exact position in the galaxy, dinosaurs dominated the planet. Mammals existed, but only as small creatures hiding in the shadows. The continents sat in different positions. The climate bore no resemblance to today. None of the species you know had evolved yet. This period is called a galactic year. It's the time required for our star and its planets to complete one full orbit around the Milky Way's center. The confirmed duration is roughly 250 million Earth years. Some estimates suggest 200 million. Others push it to 230 million. The variation comes from uncertainties in measuring both our orbital speed and the exact distance we travel. Think about what this means. Since Earth formed roughly 4.5 billion years ago, the planet has completed only about 18 orbits, 18 trips around the galaxy. Human civilization has existed for maybe 10,000 years. That's less than 1/25,000th of a single galactic year. Blink and you'd miss it. The last galactic year saw the rise and fall of entire ecosystems. The Triassic period began. Dinosaurs emerged and diversified. The supercontinent Pangaea started breaking apart. Massive volcanic eruptions reshaped the planet. The Permian extinction, the worst mass extinction in Earth's history, occurred. More than 90% of marine species vanished. Life came closer to complete annihilation than at any other time. By the time we complete the current galactic year, the continents will have drifted into unrecognizable configurations. New mountain ranges will have risen. Old ones will have eroded to nothing. Species that exist today will be extinct. New forms of life will have evolved. The climate will have shifted multiple times. Ice ages will come and go. Human civilization, if it survives, will be unrecognizable. The entirety of recorded history, from the first cities to space exploration, represents less than 1/40,000th of a galactic year. You could fit 40,000 human civilizations, each lasting as long as ours, into a single orbit. The orbital period isn't perfectly regular either. Gravitational interactions with other stars, passage through the spiral arms, and encounters with massive gas clouds all introduce tiny variations in our speed. Sometimes we move slightly faster, sometimes slightly slower. Over millions of years, these variations average out, but they're real. During the last galactic year, our star passed through the spiral arms multiple times. Each passage increased the density of nearby stars, and triggered bursts of star formation in surrounding gas clouds. Some scientists theorize that these passages could correlate with mass extinctions on Earth, though this remains controversial and unconfirmed. What will Earth look like when we return here again? Nobody knows. Nobody can predict that far into the future. But one thing is certain: 26,000 light years. You read those words and your brain processes them as information, but you don't truly comprehend what they mean. You can't. The human mind did not evolve to grasp distances measured in trillions of miles, multiplied by thousands. Let me try to help you understand. Take a commercial jet, the kind that flies you on vacation. That jet cruises at about 500 miles per hour. Now imagine pointing that jet toward the galactic center and keeping the engines running continuously, never landing, never refueling, just flying in a straight line through empty space at cruising speed. How long would it take to reach the center? Roughly 6 million years. The jet would need to fly continuously from before modern humans evolved all the way to today, and it would only be partway there. The entire span of human existence, from our earliest ancestors to the present, wouldn't cover even a fraction of the journey. Light makes the same trip in 26,000 years. But light moves at 670 million miles per hour. Nothing can move faster. Light represents the ultimate speed limit of the universe. And even light, racing through the void without rest, takes 26 millennia to reach the galaxy's heart. This means something profound. When you look toward the constellation Sagittarius, where the galactic center lies, you're not seeing what exists there now. You're seeing what existed there 26,000 years ago, before agriculture, before writing, before civilization. The light reaching your eyes tonight left the galactic core when humans were still hunter-gatherers painting on cave walls. If the galactic core exploded right now, we wouldn't know for 26,000 years. The explosion could have already happened. We'd have no warning, no sign. The light from that catastrophe is still racing toward us through the darkness, and it won't arrive for millennia beyond count. Distance and time become the same thing at this scale. Astronomy is time travel. Every distant object you observe shows you its past. The farther you look, the farther back you see. The galactic center exists in your past, permanently delayed by the speed limit of light. Radio signals travel at light speed too. If aliens at the galactic core tried to contact us today using radio waves, their message would take 26,000 years to arrive. By the time we received it and sent a reply, another 26,000 years would pass before they heard our response. A simple conversation would require over 50,000 years. The distance also affects what we can observe. Dust clouds block visible light. The galactic core is hidden behind vast sheets of interstellar material. We can only see it using infrared light, radio waves, and X-rays, which penetrate dust more easily. In visible light, the center remains invisible, shrouded in darkness, but the distance protects us too. 26,000 light-years is far enough to shield us from the violence at the core, the radiation, the gravitational chaos, the supermassive black hole consuming everything nearby. We orbit safely in the suburbs while the center rages. Yet even this enormous distance is tiny compared to what comes next. Scale models help us understand the incomprehensible, so let's shrink the galaxy. Imagine the entire Milky Way compressed down until it fits perfectly over North America. The galactic disk stretches from the Atlantic to the Pacific, from Canada to Mexico. 100,000 light-years compressed into about 3,000 miles. On this scale, our entire solar system, from our star out to the orbit of Neptune, shrinks to the size of a single blood cell, not a basketball, not a marble, a microscopic cell invisible to the naked eye. You could fit millions of solar systems across a single inch. Earth itself, Earth becomes smaller than an atom. You couldn't see it with any microscope. It would exist only as a theoretical point, a mathematical abstraction too small for physical reality to represent. Everything you know, everyone who ever lived, all of human history, compressed into less than atomic dimensions. The distance between our star and the nearest neighboring star, about 4 light-years, becomes roughly 1 inch on this scale, 1 inch of empty space between one blood cell and the next. Stars are astonishingly far apart relative to their size. The galaxy is mostly emptiness, punctuated by tiny points of light separated by cosmic voids. Our position in the Orion Arm? We'd sit somewhere over Kansas. The galactic center would lie near Washington, D.C. on the east coast. The edge of the galaxy would reach Los Angeles on the west coast. The supermassive black hole at the core, which we'll explore later, would be smaller than a grain of sand sitting in the nation's capital. But here's what breaks your intuition. On this scale, the galaxy's thickness, that 1,000 light-year thin disk, would measure only 30 miles. Picture North America compressed down to a sheet of glass 30 miles thick. That's the structure we live inside. A continent-sized window pane floating through space. The spiral arms would appear as slightly denser regions of blood cells, zones where the concentration increases, but individual cells remain separated by vast emptiness. The arms don't touch. They're not solid. They're just probability waves, regions where stars cluster slightly closer together than average. Other galaxies exist on this scale too. Andromeda, our nearest large neighbor, would sit roughly 250,000 miles away, about the distance from Earth to our actual natural satellite. Andromeda is close, dangerously close. It's already approaching, and collision is inevitable. The local group of galaxies, which includes the Milky Way, Andromeda, and several dozen smaller galaxies, would fit inside a sphere about 3 million miles across. All the galaxies we consider neighbors, all the stellar systems we interact with gravitationally, contained in a region less than the distance between Earth and our actual star. This scale model breaks down when you try to include the entire universe. Even compressed to this degree, the observable universe would still extend trillions of miles in every direction. The scale required to visualize everything is too extreme. The numbers stop making sense. But right now, focus on that blood cell hovering over Kansas. That's your home. That's everything you know. And we haven't even discussed the details yet. Count to 10. It takes roughly 10 seconds. Count to 100, maybe 2 minutes. Now try counting to 1 billion. Don't actually try. You'd need 32 years if you counted one number per second without sleeping. You'd die of old age before finishing. The Milky Way contains between 100 billion and 400 billion stars. The exact number remains uncertain because faint stars are nearly impossible to detect at great distances. But even the conservative estimate of 100 billion should shatter your sense of significance. 100 billion stars means 100 billion stellar systems. Most stars have planets. Recent observations confirm that planetary systems are the rule, not the exception. This suggests at least 100 billion planets exist in our galaxy alone. Many of those planets orbit in habitable zones where liquid water could exist. Earth is one planet among 100 billion. Our star is one among 100 billion. You are one organism among billions, on one planet among billions, orbiting one star among billions. The layers of insignificance stack up until meaning dissolves. But let's make this more visceral. Imagine every star in the galaxy is a grain of sand. You'd need enough sand to fill several Olympic swimming pools. Now imagine trying to find one specific grain of sand in those pools. That's the challenge of locating our star from outside the galaxy. We'd be indistinguishable from the background, lost in the crowd. The stars aren't evenly distributed either. The central bulge contains the highest density. Billions of stars pack into a relatively small volume, far more crowded than our suburban neighborhood. Out in the spiral arms, stars spread thinner. The spaces between them widen. But even in the sparsest regions, you'd still find millions of stars within a sphere just a few hundred light-years across. Different types of stars populate different regions. The disk contains young, hot stars burning blue and white. These stars formed recently from gas clouds and haven't had time to age. The central bulge glows yellow and red with ancient stars billions of years old. These stars formed when the galaxy was young, when the universe contained less heavy elements. Some stars move faster than others. High-velocity stars, kicked out of their original orbits by gravitational encounters, zip through the galaxy at extreme speeds relative to their neighbors. Hypervelocity stars move so fast, they'll eventually escape the galaxy entirely, flung out into intergalactic space by close encounters with the supermassive black hole at the core. Binary star systems are common. More than half of all stars have at least one companion. Some stars orbit in triple or quadruple systems, complex gravitational dances that make stable planetary orbits nearly impossible. A few stars exist in clusters containing thousands of siblings, all born from the same gas cloud. But most stars are dim. Red dwarfs, the smallest and faintest stars, outnumber all other types combined. They burn so slowly, they'll outlive the universe's current age. Stars like ours, yellow dwarfs, represent a minority. Massive blue giants, the brightest stars, are the rarest of all and burn out quickly. And among all these stars, all these worlds, all this vastness, how many civilizations might exist? How many are looking up at their sky right now, asking the same question we are? You've seen images of the Milky Way, beautiful spiral arms curling outward from a bright core, photographed from an impossible angle. But those images are artists' renderings, educated guesses, informed approximations. Nobody has ever photographed our galaxy from outside because getting outside is impossible. We live inside the structure we're trying to map. It's like being trapped inside a house and trying to describe what the house looks like from the street. You can measure room dimensions. You can count the floors, but you can't see the exterior. You can't verify the roof's shape or determine the color of the siding. For most of human history, we didn't even know we lived in a galaxy. The Milky Way band stretching across the night sky was mysterious. Some cultures thought it was milk spilled by gods. Others called it a river of light. The ancient Greeks gave it the name we still use, but nobody understood what they were seeing. Only in the early 20th century did astronomers confirm that the Milky Way is a galaxy, one among billions. Edwin Hubble proved that other galaxies exist beyond our own. Suddenly, our entire cosmic neighborhood was recontextualized. We weren't looking at the edge of the universe. We were looking at the edge of our own island, one structure among countless others. Mapping the spiral arms required decades of painstaking work. Astronomers used radio telescopes to detect neutral hydrogen gas clouds. Gas concentrates in spiral arms, marking their locations. By measuring the distances to these clouds and tracking their motions, scientists slowly reconstructed the galaxy's structure. The work is still ongoing. Recent observations suggest the Milky Way has 4 major spiral arms, not 2 as once thought. The Scutum Centaurus arm and the Perseus arm are well established. The Sagittarius arm and the Norma arm round out the quartet, but details remain fuzzy. The exact number of minor arms and spurs is still debated. Our location in the Orion spur makes mapping even harder. We sit inside a minor feature, surrounded by dust and gas that blocks our view in multiple directions. Looking toward the galactic center, we see only a few thousand light-years before interstellar dust absorbs all visible light. The core remains hidden unless we switch to infrared or radio wavelengths. Looking outward toward the galaxy's edge presents different challenges. Fewer stars exist in that direction. Distances become harder to measure. The edge of the disk is not sharp. It fades gradually into the halo, making it impossible to define precisely where the galaxy ends. If we could somehow launch a spacecraft fast enough to escape the galaxy and photograph it from a distance, the journey would take millions of years. Even traveling at light speed, leaving the galaxy and reaching a vantage point far enough away to see the full structure, would require a 100,000-year journey. By the time the spacecraft sent back images, human civilization might no longer exist. So we're stuck guessing, building models, comparing our galaxy to others we can see, assuming that what we observe in distant spirals applies to our own. It's frustrating, it's limiting, but it's the only method available. And there's something else we can't see, something far more massive than all the stars combined. At the center of the Milky Way sits a black hole so massive it defies intuition. Its name is Sagittarius A star, often written as an abbreviation. The mass of this object equals roughly 4 million times the mass of our star. 4 million stellar masses compressed into a region smaller than the orbit of Mercury. This is confirmed, not theoretical, not hypothetical. Astronomers have tracked individual stars orbiting this black hole for decades. They've measured orbital periods, speeds, and distances. The math is undeniable. Only a black hole could produce the gravitational effects observed. The black hole's event horizon, the point of no return where escape becomes impossible, has a radius of roughly 7 million miles. That's small by galactic standards. You could fit this black hole inside the distance between our star and the planet Mercury. Yet its gravitational influence extends across thousands of light years. Scientists captured the first image of this black hole in 2022 using the Event Horizon Telescope, a network of radio observatories spread across Earth. The image shows a bright ring of superheated gas surrounding a dark shadow. The shadow is the black hole itself, a region so gravitationally intense that not even light can escape. The bright ring is material falling inward, accelerated to near light speed and heated to billions of degrees. The black hole is mostly dormant now. It consumes relatively little material compared to supermassive black holes in other galaxies. But evidence suggests it wasn't always quiet. About 200 years ago, the black hole experienced a major outburst, consuming a large amount of gas and radiation that we're only now detecting as it reflects off nearby clouds. What triggered that feeding frenzy remains unknown. Stars orbit this monster on frighteningly tight paths. One star, designated by astronomers with a simple letter and number combination, completes an orbit in just 16 years. 16 years to circle a black hole at distances closer than Pluto orbits our star. The speed required for such an orbit approaches 3% of light speed. The star experiences relativistic effects, time dilation, and gravitational redshift as it whips around the black hole. During close approach, the star passes within just 17 light hours of the event horizon. At that distance, tidal forces nearly tear the star apart. The difference in gravitational pull between the star's near side and far side is immense. Only the star's internal structure and orbital speed prevent complete destruction. Watching these stars orbit has allowed scientists to test Einstein's general relativity in extreme conditions. Predictions about orbital precession, gravitational time dilation, and light bending all match observed reality. General relativity remains undefeated, but we're pushing it to its limits. Thousands of smaller black holes orbit the supermassive one. These stellar mass black holes, the remnants of massive stars, cluster near the galactic core where star density peaks. They form a dangerous neighborhood, a region where gravitational interactions are common and violent. Gas clouds occasionally wander too close to the central black hole. Astronomers watch them get torn apart by tidal forces, stretched into long filaments before vanishing across the event horizon. One cloud passed close enough a few years ago that scientists predicted its complete destruction. It survived. How? Mystery. What happens to matter that crosses the event horizon? Unknown. General relativity predicts a singularity, a point of infinite density where physics breaks down. But quantum mechanics suggests something else might occur. Nobody knows. Nobody can observe what happens inside. And this black hole is considered small. Some galaxies harbor black holes billions of times our star's mass. But for us, this is the monster we orbit. This is the anchor holding our galaxy together. There are stars near the galactic center that move so fast they seem impossible. Stars racing around the supermassive black hole at speeds that make our orbital velocity look glacial. One star completes its entire orbit in 16 years, 16 Earth years from start to finish. Our star takes 250 million years to orbit once. This star does it in 16. The speed difference is incomprehensible. The star reaches roughly 3% of light speed at its closest approach to the black hole. That's nearly 6 million miles per hour. Nothing in our solar system comes remotely close to these velocities. Astronomers have tracked this star since the 1990s. They've watched it complete multiple orbits now. Its path is highly elliptical. At its farthest point, it ventures out relatively far from the black hole. At its closest approach, called perinegricon in astronomical terminology, it dives within 17 light hours of the event horizon. What does 17 light hours mean? It's the distance light travels in 17 hours, roughly 11 billion miles. That sounds far until you remember the black hole's event horizon is only 7 million miles across. The star passes just a few hundred times the black hole's radius. In cosmic terms, that's skimming the surface. At closest approach, the star experiences gravitational forces that warp spacetime itself. Time passes slower for the star than for distant observers. This is confirmed time dilation, a prediction of general relativity. If you could somehow stand on that star during perinegricon, you'd age slightly slower than people far from the black hole. The effect is tiny but measurable. The star's light also experiences gravitational redshift. As photons climb out of the deep gravitational well, they lose energy and shift toward longer, redder wavelengths. Astronomers measure this shift and use it to confirm the black hole's mass. Every observation adds more precision to our understanding. Tidal forces at perinegricon should tear the star apart. The gravitational pull on the star's near side is significantly stronger than the pull on its far side. This difference, the tidal force, stretches the star, yet it survives. Its internal structure and rapid orbital motion save it from destruction. Multiple stars orbit at similar distances. Scientists have catalogued dozens of these high-velocity objects, each designated with simple alphanumeric codes. They're called stars, and they represent a unique laboratory for testing extreme physics. No other location in the galaxy offers such extreme conditions at accessible observation distances. Some of these stars are so close to the black hole that their orbits precess measurably. Precession means the orbit itself rotates over time, like a spirograph drawing. General relativity predicts this effect near massive objects. Observations match predictions perfectly. Einstein was right again. How did stars get into such dangerous orbits? Two theories dominate. Either they formed farther out and were gravitationally kicked inward through interactions with other stars, or they formed in a disk of gas around the black hole itself. Both scenarios are plausible. Neither is confirmed. What's certain is that these stars won't survive forever. Eventually, gravitational interactions will either fling them out of the galactic core or send them plunging across the event horizon. Their current orbits are temporary, cosmically speaking, but for now, they provide our best view of black hole physics, and their existence proves something else. The galactic core is far more dangerous than our safe suburban orbit. We orbit 26,000 light-years from the galactic center. This distance isn't random. It's not accidental. Our location in what astronomers call the galactic suburbs offers unique advantages that make complex life possible. Move significantly closer or farther out, and conditions change dramatically. The galactic core is violent. Star density peaks there. Stars pass close enough to disturb each other's planetary systems gravitationally. Planets get ejected into interstellar space. Stellar collisions, though rare, occur more frequently than anywhere else in the galaxy. Close binary stars merge. Black holes consume gas clouds and occasional stars. Radiation at the core is intense. The supermassive black hole emits X-rays and gamma rays. Supernovae, the explosive deaths of massive stars, happen more often in regions of high star density. Each supernova releases radiation that sterilizes nearby planets. The background radiation level near the core is thousands of times higher than in our neighborhood. If Earth orbited a star near the galactic center, life as we know it couldn't exist. The radiation would break down complex molecules. Atmospheric chemistry would be disrupted. Mutations would occur too rapidly for evolution to stabilize. Any biosphere would be repeatedly reset by nearby stellar violence. Moving too far outward presents different problems. The outer edge of the galaxy contains fewer stars. Heavy elements, the building blocks of planets and life, are scarcer. Stars in the outer regions formed from gas clouds with lower metallicity. Astronomers speak for elements heavier than hydrogen and helium. Rocky planets like Earth might not form at all in those regions. Our distance from the center places us in the galactic habitable zone, a theoretical region where conditions favor complex life. We're far enough from the core to avoid its radiation and gravitational chaos, yet close enough to benefit from the chemical enrichment produced by generations of stars. This is the sweet spot. The spiral arm structure matters too. We sit inside the Orion Spur, a minor arm between two major ones. This location means we don't spend much time crossing through the denser regions of major spiral arms, where supernova rates increase. We avoid the most dangerous neighborhoods while still residing in a region rich with stars. Our star's orbit is nearly circular, another rare advantage. Many stars follow highly elliptical paths that carry them through spiral arms regularly. Our stable, circular orbit keeps conditions relatively constant. We don't experience extreme variations in stellar density or radiation exposure as we circle the galaxy. The local bubble, a region of low-density space carved out by ancient supernovae, surrounds our solar system. This bubble extends hundreds of light years in all directions. It's a protective cocoon, a region where interstellar gas and dust are thinner than average. This thinness reduces the friction our star experiences as it moves through space. Everything about our location suggests remarkable luck. We orbit in a relatively safe zone. We avoid the core's violence. We benefit from chemical enrichment. Our orbit is stable and circular. The local bubble protects us. Stack up all these factors, and you realize how rare our situation might be. How many other stars enjoy similar advantages? Unknown, but the percentage is likely small. Most stars orbit in less favorable conditions. They experience higher radiation, greater gravitational disturbance, or insufficient heavy elements for planet formation. And yet, despite our privileged location, we're still just one star among billions. Our neighborhood might be safe, but it's not special. We're suburbanites in a city of stars, comfortable but unremarkable, which brings us to the structure we live inside. The galaxy is mostly empty space. Between stars, vast voids stretch for light years, but the stars themselves, along with their gas and dust, concentrate in specific regions. The primary region is the thin disk, and it's far thinner than most people imagine, 1,000 light-years thick at the spiral arms. That's the disk's vertical dimension. Compare this to the galaxy's diameter of 100,000 light-years. The ratio is 1 to 100. Imagine a dinner plate as wide as a football field. That's the galaxy's proportions. A cosmic pancake so flat, it challenges comprehension. This flatness arises from rotation. When the galaxy formed billions of years ago, gas and dust swirled around the developing center. Gravity pulled material inward. Angular momentum, the tendency of spinning things to keep spinning, prevented complete collapse. The result is a rotating disk, the most stable configuration for a spinning system. Within this disk, stars orbit the galactic center on roughly circular paths. Each star maintains a nearly constant distance from the core, like cars on a circular racetrack. But unlike cars, Stars don't travel in packs. Each follows its own independent orbit. Sometimes orbits cross. Stars pass near each other, exchange gravitational energy, and drift to new orbits. The thin disk contains the youngest stars, hot blue giants, blazing white stars, and yellow stars like ours populate this region. These stars formed relatively recently from gas clouds within the disk itself. Star formation continues today wherever gas clouds collapse under their own gravity. Gas and dust also concentrate in the thin disk. Vast molecular clouds, nurseries where new stars are born, float through the galactic plane. These clouds are cold and dense. When they collapse, they fragment into clumps that ignite as new stars. The process has continued for billions of years and will continue for billions more. The disk isn't perfectly smooth. Density variations create the spiral arms. Gas clouds pile up in certain regions, triggering bursts of star formation. These regions glow brightly because massive young stars shine intensely but briefly. The spiral arms appear bright primarily because of these young stars, not because they contain fundamentally more stars overall. Above and below the thin disk lies the thick disk, a puffier region containing older stars. These stars were born in the thin disk but got kicked out vertically by gravitational interactions. They orbit on paths tilted relative to the galactic plane, creating a halo of stars above and below the main structure. The thick disk is roughly twice as thick as the thin disk, but contains fewer stars overall. Its stars are older and redder. They formed when the galaxy was younger and have been wandering ever since. Some orbit at angles so steep they barely pass through the thin disk at all. Our position within the thin disk, just 55 light-years above the midplane, means we're embedded in the densest stellar population. When you look at the Milky Way band across the night sky, you're seeing this disk edge on. The combined light of billions of stars compressed into that thin structure creates the glowing band. But the disk only accounts for a fraction of the galaxy's mass. Most of the mass exists in a completely different form, a form we cannot see. 90% of the galaxy's mass is invisible, completely invisible. It emits no light. It reflects no light. It absorbs no light. We know it exists only through its gravitational effects. This mysterious substance is called dark matter, and it dominates the Milky Way. Here's how we discovered it. Astronomers measured the rotation speeds of stars at different distances from the galactic center. They expected outer stars to orbit more slowly than inner stars, following the same physics that governs planets in our solar system. Neptune orbits slower than Earth because it's farther from the gravitational source. But the galaxy doesn't work that way. Stars near the edge orbit almost as fast as stars closer to the center. The rotation curve stays flat instead of declining. This should be impossible. The visible matter in the galaxy can't produce enough gravity to keep outer stars moving so fast. They should fly off into space. 3 explanations exist. Either our understanding of gravity is wrong, the galaxy contains far more mass than we can see, or something else we haven't discovered is happening. Most astronomers favor the second option. There must be additional mass, distributed in a roughly spherical halo around the visible galaxy. This invisible mass is dark matter. How much dark matter exists? Current estimates suggest the dark matter halo contains roughly 10 times the mass of all visible stars combined. The halo extends far beyond the visible disk, possibly stretching hundreds of thousands of light-years from the galactic center. We orbit inside this halo. We're surrounded by invisible mass we cannot detect directly. What is dark matter made of? Unknown. Decades of experiments have failed to detect dark matter particles directly. We know it's not ordinary matter like protons and neutrons. It doesn't interact with light at all. It passes through normal matter without collision, like ghosts passing through walls. Dozens of theories attempt to explain dark matter. Some propose exotic particles created in the early universe. Others suggest modifications to gravity itself. A few radical ideas even question whether dark matter exists at all, proposing instead that our observations are misinterpreted. but the gravitational evidence is overwhelming. Something is there. The Milky Way's dark matter halo acts like invisible scaffolding. It holds the galaxy together. It prevents outer stars from escaping. It anchored the galaxy's formation billions of years ago when gas collapsed to form the first stars. Without dark matter, galaxies as we know them couldn't exist. Other galaxies also have dark matter halos. Small dwarf galaxies appear to be dominated by dark matter, containing almost nothing else. Massive galaxy clusters hold enough dark matter to bend light from background galaxies gravitationally, creating distorted images visible through telescopes. The presence of dark matter affects everything in the galaxy: star orbits, gas cloud movements, the formation of spiral arms, even the motions of satellite galaxies orbiting the Milky Way. Dark matter's gravity influences structures across all scales. Despite years of searching, dark matter remains elusive. Particle detectors buried deep underground wait for collisions that never come. Space telescopes look for annihilation signatures. Colliders smash particles together, hoping to create dark matter in the debris. So far, nothing. We live in a galaxy whose mass is mostly mystery. The stars, planets, gas, and dust we can see represent only 10% of the total. The rest is invisible, undetectable, and entirely unknown. It's a humbling reminder of how little we truly understand, but the space immediately around us holds its own mysteries. You orbit inside a bubble, not a physical bubble, a region of space carved out by violence. Roughly 1,000 light-years across, this cavity contains almost no interstellar gas or dust. It's called the local bubble, and understanding its origin requires understanding stellar death. Millions of years ago, multiple massive stars in our galactic neighborhood reached the end of their lives. Massive stars burn through their fuel quickly, living only a few million years before exploding as supernovae. When these stars exploded, they released shock waves that swept through surrounding space at thousands of miles per second. These shock waves compressed and heated the interstellar medium, the thin gas between stars. The heated gas expanded rapidly, pushing outward and creating a bubble. Over millions of years, the bubble grew. More supernovae detonated inside the expanding cavity, adding energy and pushing the walls outward further. Today, the local bubble extends hundreds of light years in all directions from our position. The interior contains gas at roughly 1,000,000 degrees, hot enough that it emits faint X-rays. But the density is extremely low. Only a few atoms exist per cubic centimeter, compared to thousands in denser regions of the galaxy. Our location near the bubble's edge places us in a fortuitous position. We're close enough to benefit from the reduced gas density, which makes observing distant stars easier, but far enough from the bubble's origin that we avoided the worst radiation from the ancient supernovae. The bubble's walls contain denser gas clouds where new stars are forming. These clouds were compressed by the expanding shock waves, triggering gravitational collapse. Young star clusters dot the bubble's perimeter. Many of the brightest stars in our night sky, the ones you recognize in constellations, sit on the local bubble's shell. This structure is not unique. The galaxy is riddled with similar bubbles created by stellar explosions. They overlap and interact, creating a foamy structure in the interstellar medium. Some bubbles are larger, others smaller. The local bubble just happens to be the one containing our solar system. Movement through the bubble affects our star. As our solar system orbits the galaxy, it plows through whatever thin gas exists along its path. This creates a bow shock, like the wake of a boat moving through water. Our star's magnetic field and solar wind push against the interstellar medium, forming a protective boundary called the heliosphere. The heliosphere shields us from cosmic rays, high-energy particles that would otherwise bombard Earth more intensely. This shielding varies depending on the density of surrounding space. Inside the local bubble, where density is low, the heliosphere extends farther. In denser regions, it compresses. Scientists recently mapped the local bubble in 3 dimensions using data from multiple telescopes and satellites. The structure is not spherical, it's elongated and irregular, shaped by the specific locations and energies of the supernovae that created it. We're currently moving toward one of the bubble's walls, though we won't reach it for millions of years. The bubble's existence raises questions about our past and future. Did ancient supernovae affect Earth's climate or biosphere? Some scientists theorize that gamma rays from nearby stellar explosions could have triggered mass extinctions or genetic mutations. The evidence is inconclusive, but the possibility is real. Will more supernovae explode nearby? Probably. Massive stars still exist in our neighborhood. When they explode, they'll add energy to the bubble or create new cavities. The local bubble will evolve, reshape, and possibly merge with adjacent structures. For now, we drift through this ancient cavity, protected by emptiness itself. But just how small is the space we actually see? Let's try another scale comparison, because the first one probably didn't break your brain enough. This time, we'll make Earth the reference point. Shrink Earth down to the size of a grain of salt. That tiny crystal you can barely see on your fingertip, that's our entire planet on this new scale. On this scale, our star becomes roughly the size of a ping pong ball. The distance between Earth and our star? About 8 feet. You could walk it in 3 steps. The entire solar system, from our star out to Neptune's orbit, fits inside a typical suburban house. Pluto's orbit reaches maybe into the front yard. Now, here's where it gets disturbing. The nearest star system sits roughly 300 miles away on this scale. 300 miles of absolutely nothing. Empty space, stretching from one ping pong ball to the next. No planets between them. No asteroids. Just void. That's how sparse stars are distributed through the galaxy. The Milky Way's disk, on this scale, would stretch roughly 5 million miles across, about 20 times the distance from Earth to our actual natural satellite. The thickness of that disk? Only 50,000 miles, still paper-thin relative to its width, a cosmic blade stretching across space. But Earth is a grain of salt in this model. One grain among countless others. If you spread grains of salt across this entire 5 million mile disk, with each grain representing a planet, you'd need hundreds of billions of them. Finding the specific grain that represents Earth would be impossible. You'd search forever and never locate it. This scale reveals something crucial about space travel. The distances between stars are so vast that even moving at light speed requires years. Chemical rockets, the kind we currently build, would take tens of thousands of years to reach even the closest neighboring system. Humans would need to live and die aboard generation ships, with only distant descendants arriving at the destination. No known technology can bridge these gaps quickly. Warp drives remain science fiction. Wormholes are theoretical curiosities with no experimental basis. Suspended animation might work for biological organisms, but it doesn't change the fundamental problem of distance. Space is simply too large. Some people imagine interstellar highways connecting star systems. They picture traffic flowing between worlds like ships crossing oceans. But ocean crossings take days or weeks. Interstellar crossings take centuries or millennia. The scale difference is so extreme that analogies break down. Even communication across these distances becomes nearly impossible. A message sent to the nearest star takes over 4 years to arrive. The reply takes another 4 years to return. A simple conversation requires nearly a decade. Coordinating any kind of relationship or commerce across light years seems absurd. The galaxy is fundamentally lonely. Stars are islands separated by oceans of darkness. Whatever life exists on other worlds will likely remain isolated forever, unable to bridge the gulfs between systems. We may never meet our galactic neighbors. The distances are too great, and Earth, that grain of salt, sits in the middle of all this emptiness, orbiting one ping pong ball among hundreds of billions, utterly alone and completely invisible from any distance worth mentioning. But at least we have neighbors in the form of massive structures nearby. The Orion Spur sits between two much larger structures. These are the major spiral arms that dominate our region of the galaxy. To our galactic north lies the Perseus Arm. To our south curves the Sagittarius Arm. Both dwarf our modest neighborhood in size and stellar population. The Perseus Arm stretches thousands of light-years in length and hundreds of light-years in width. It's one of the galaxy's two primary spiral arms, containing billions of stars, countless gas clouds, and active star formation regions. When you look at images of distant spiral galaxies, the bright arms you see are structures like Perseus, dominant features that define the galaxy's appearance. This arm sits roughly 6,500 light-years farther from the galactic center than we do. That might sound like a safe distance until you remember that galactic structures don't have sharp boundaries. The outer edge of the Perseus Arm approaches our position. We're close enough to see stars within it, close enough to feel its gravitational influence subtly. Star formation in the Perseus Arm outpaces formation in the Orion Spur. Massive molecular clouds collapse more frequently there. Young star clusters blaze with blue and white light. These regions are violent nurseries where stellar birth and death happen on accelerated timescales. Supernovae detonate regularly, seeding the arm with heavy elements. The Sagittarius Arm curves inward toward the galactic core. It sits closer to the center than we do, wrapping around the galaxy's heart like a spiral staircase. This arm contains similar stellar populations to Perseus, but occupies a more dangerous neighborhood. Proximity to the core means higher radiation levels, more frequent stellar interactions, and greater gravitational complexity. Between these two giants, the Orion Spur looks almost accidental. Some astronomers questioned whether it qualified as a true arm or was merely a bridge connecting Perseus and Sagittarius. Recent measurements suggest it's substantial enough to merit arm status, but it remains the smaller sibling in this family. The spiral arms are not solid structures. Stars don't stay locked in fixed positions within them. Instead, the arms are density waves, regions where stars temporarily cluster as they orbit. Think of it like traffic on a circular highway. Cars bunch up in certain sections, creating apparent structures that move around the loop even though individual cars pass through. This means stars drift in and out of spiral arms over millions of years. Our star has passed through spiral arms multiple times during its lifetime. Each passage increased the local stellar density temporarily, exposing us to more nearby stars and slightly higher supernova risk. But these passages are brief on galactic timescales. The gravitational influence of spiral arms affects more than just stellar orbits. Gas clouds get compressed as they enter the arms, triggering star formation. This is why arms appear bright in photographs. They're not denser in total mass by huge margins, but they contain more young, luminous stars that dominate visible light. As our solar system orbits, we're currently moving toward the Perseus Arm. Millions of years from now, we'll pass through its outer regions. The stellar density around us will increase slightly. More nearby stars will become visible. The risk of supernova exposure will rise temporarily. Then we'll emerge on the far side and drift toward the outer galaxy. This cycle has repeated throughout Earth's history. Our planet has seen many different stellar neighborhoods. The night sky looked different in the past and will look different in the future. Constellations change. Nearby stars come and go. The only constant is motion. Living between major arms offers protection. We avoid the densest regions where stellar violence peaks, but we're close enough to benefit from chemical enrichment. It's another example of our fortunate location. But location is only part of the story. Understanding the full structure requires looking at the galaxy from outside. Imagine you could leave the galaxy, board a faster-than-light spacecraft, and travel outward at impossible speeds. As you climb away from the galactic plane, the disk begins to reveal itself. First, you see your local neighborhood from above, then wider regions come into view. Eventually, the entire structure spreads beneath you like a cosmic pinwheel. From this impossible vantage point, the Milky Way looks flatter than you imagined. The disk appears almost two-dimensional, a thin sheet of light extending in all directions. The central bulge interrupts the flatness, glowing yellow and orange with ancient starlight. But beyond the bulge, the disk dominates. 4 spiral arms curl outward from the center. 2 major arms, Perseus and Scutum Centaurus, define the structure. 2 smaller arms, Sagittarius and Norma, fill the gaps. The Orion Spur, where Earth resides, appears as a minor diagonal bridge, barely visible compared to the major features. You'd need to zoom in considerably to pick out our location. The arms don't touch. Gaps exist between them, regions of lower stellar density where stars spread thinner. These inter-arm regions are dimmer, harder to see, but they still contain billions of stars. The arms stand out primarily because of young, massive stars that burn intensely but briefly. Colors vary across the disk. The core glows red and yellow, dominated by ancient stars billions of years old. The spiral arms blaze blue and white where young stars formed recently. Between the arms, colors shift toward yellow and orange, indicating intermediate age stellar populations. The galaxy is a rainbow of stellar evolution, each color telling a different story. Dust lanes trace the spiral arms' inner edges. These dark regions block visible light, creating intricate patterns of shadow and illumination. The dust isn't uniformly distributed. It clumps into clouds and filaments, obscuring background stars and creating stunning contrasts between light and dark. The disk is not perfectly flat, even from this perspective. Warps and ripples disturb the plane, likely caused by gravitational interactions with satellite galaxies orbiting the Milky Way. The outer disk bends slightly upward on one side, downward on the other. It's like a vinyl record left in the heat, deformed but still functional. Beyond the visible disk, the dark matter halo extends invisibly outward. You can't see it, but its gravitational influence shapes everything. The halo is roughly spherical, encompassing the disk and bulge like an enormous bubble. Its outer boundary remains undefined, fading gradually into intergalactic space. Satellite galaxies orbit in the halo, small dwarf galaxies containing millions or billions of stars each, circle the Milky Way like moons around a planet. The 2 largest, visible from Earth's southern hemisphere, are the Magellanic Clouds. They orbit roughly 160,000 light-years from the galactic center, well outside the visible disk. The Milky Way is consuming some of these satellites. The closest dwarf galaxy is being torn apart by tidal forces, its stars stripped away and absorbed into the galactic halo. This process has happened many times throughout the galaxy's history. Small galaxies merge into larger ones, contributing their stars and gas to the growing structure. From even farther away, the Milky Way begins to look small. Other galaxies appear in the distance. Andromeda, roughly 2.5 million light-years away, dominates the view. It's nearly twice the Milky Way's size, a massive spiral heading toward inevitable collision. Smaller galaxies dot the space between them. Members of the local group bound together gravitationally. Pull back further, and the Milky Way becomes just one galaxy among thousands in the local supercluster. Individual features vanish. The spiral arms disappear. Even the galactic bulge shrinks to insignificance. What seemed enormous from inside becomes a tiny smudge of light among countless others. But you can't actually make this journey. You're trapped inside the structure you're trying to observe. So astronomers improvised. At the galaxy's heart, before you reach the supermassive black hole, sits a vast sphere of ancient stars. This is the central bulge, and it represents the galaxy's oldest component. 10,000 light-years in diameter, this structure formed when the universe was young and has persisted ever since. The bulge glows yellow and orange. These colors indicate old stellar populations. Red giants dominate the bulge, massive stars in their final evolutionary stages that have swollen to enormous sizes. Yellow stars like ours exist here too, but aged billions of years. Blue stars, the young hot ones that populate spiral arms, are almost entirely absent. Why the age difference? Star formation in the bulge ended long ago. The gas and dust required for making new stars were either consumed in ancient stellar births or expelled by stellar winds and supernovae. What remains is a population of ancient survivors, stars that formed when the galaxy first assembled. The bulge contains roughly 20 billion stars. That's a small fraction of the galaxy's total population, but packed into a relatively tiny volume. Stellar density in the bulge exceeds density in the disk by factors of hundreds or thousands. Stars crowd together more tightly than anywhere else in the galaxy except the immediate vicinity of the central black hole. If Earth orbited a star in the bulge, the night sky would look completely different. Instead of a few thousand visible stars, millions would be bright enough to see with naked eyes. The sky would never be truly dark. Even at midnight, the combined light of nearby stars would create a permanent twilight. Reading by starlight would be trivial, but conditions in the bulge are hostile to life as we know it. The stellar density increases collision risks. Planetary systems get disrupted by passing stars more frequently. Gravitational interactions eject planets from their orbits or send them plunging into their parent stars. Stable conditions, the kind required for billions of years of biological evolution, are rare. Radiation levels are higher too. More stars mean more supernovae. More supernovae mean more high-energy particles flooding the interstellar medium. Any planet's atmosphere would face constant bombardment from cosmic rays. Mutation rates would soar. Complex life might struggle to evolve or survive. The bulge is not perfectly spherical. It's bar-shaped, elongated along one axis. This bar structure is common in spiral galaxies. Roughly 2/3 of all spirals display central bars. The bar rotates as a unit, its stars locked into resonant orbits that maintain the shape over billions of years. The bar's exact dimensions remain debated. Estimates range from 3,000 to 16,000 light-years in length. Measuring the bar's size is difficult because we view it from inside the disk, not from a clear external perspective. Different measurement techniques yield different results. This bar plays a crucial role in galactic dynamics. It funnels gas inward toward the central black hole, feeding the monster at the core. It also affects stellar orbits throughout the inner galaxy, creating resonance patterns that influence spiral arm structure. The bar is not static. It evolves slowly over hundreds of millions of years. Astronomers initially didn't realize the Milky Way had a central bar. The discovery came gradually as infrared telescopes pierced the dust, obscuring our view of the core. Infrared light passes through dust more easily than visible light. Once astronomers could see the bulge clearly, the bar structure became obvious. The bulge also contains globular clusters, ancient stellar cities orbiting in the galactic halo. These clusters are some of the oldest objects in the universe, formed shortly after the first galaxies assembled. Each cluster contains hundreds of thousands of stars, bound together gravitationally in a sphere just tens of light years across. From the bulge outward, the galaxy transitions gradually into the disk. No sharp boundary exists. The stellar populations blend together, old stars mixing with younger ones in the inner disk. Only by studying stellar ages and compositions can astronomers distinguish where the bulge ends and the disk begins. And beyond our galaxy, a neighbor approaches with terrifying inevitability. 2.5 million light-years away, a giant rushes toward us. The Andromeda Galaxy, our nearest large neighbor, is heading for collision. The impact is inevitable. The timing is roughly 4.5 billion years from now. The result will reshape both galaxies beyond recognition. Andromeda is massive. Its diameter exceeds ours by nearly a factor of 2. It contains roughly 1 trillion stars compared to our few hundred billion. Its supermassive black hole outweighs ours by tens of millions of solar masses. In almost every measurable way, Andromeda dwarfs the Milky Way. The collision has already begun, in a sense. The gravitational influence of two galaxies this massive extends across millions of light years. Even now, subtle tidal forces are pulling at each galaxy's outer regions. Stars at the edges feel the attraction of the approaching giant. Gas clouds at the periphery experience slight acceleration toward the collision point. When galaxies collide, stars rarely hit each other. The distances between stars are too vast. Most stars will pass through the opposite galaxy without ever coming close to another star. But gravitational chaos will reign. Stellar orbits will be disrupted violently. Stars will be flung in random directions, ejected from their original positions. Some stars will be cast out entirely, thrown into intergalactic space with enough velocity to escape both galaxies. These rogue stars will drift alone through the void forever, orphaned by gravitational violence. Other stars will fall toward the merged core, joining a new, larger galactic center that forms from the collision. Gas clouds will collide spectacularly. Unlike stars, gas clouds are large and diffuse enough to actually hit each other. When they do, shock waves will compress the gas, triggering enormous bursts of star formation. The merged galaxy will blaze with the light of billions of newly formed stars. This starburst phase will last millions of years before the gas supply depletes. Our solar system's fate during this collision is uncertain. Most likely, our star will be thrown into a new orbit, possibly much farther from the galactic center or much closer. There's a small chance we'll be ejected entirely, cast into intergalactic space. But direct collision with another star remains extraordinarily unlikely. Earth, if it still exists in 4.5 billion years, will have other problems. Our star will be approaching the end of its main sequence lifetime, beginning its transformation into a red giant. The collision's effects on Earth will likely be secondary compared to the dying star's expansion, but the night sky will become unrecognizable. The merged galaxy will no longer be a spiral. Collisions destroy spiral structure, scrambling stars into a more spherical configuration. The result will be an elliptical galaxy, a roughly spherical ball of stars with little internal structure. Spiral arms, the defining feature of both progenitor galaxies, will vanish. Astronomers have already named the merged galaxy. They call it Milky, a combination of both names. This future mega-galaxy will rank among the largest in the local group, potentially even in the local supercluster. It will be a giant, dominating its cosmic neighborhood. Other galaxies in the local group will eventually merge with Milky too. The Triangulum galaxy, the third largest in the local group, will either collide with Andromeda before it reaches us, or join the merger afterward. Smaller dwarf galaxies will be consumed one by one. The final result will be a single massive elliptical galaxy containing almost all the local group's mass. This is the fate of most galaxies. In regions of the universe where galaxies cluster densely, mergers happen frequently. The universe's largest galaxies formed through countless mergers over billions of years. Each collision added mass, stars, and gas, building galactic giants. The Milky Way itself has merged with other galaxies in the past. Evidence of ancient collisions hides in stellar orbits and chemical compositions. The galaxy is a construction project billions of years in progress, built from smaller components that crashed together and stuck. And the Milky Way is just one galaxy among many in an even larger structure. The Milky Way does not drift through space alone. It belongs to a cluster of roughly 30 galaxies bound together gravitationally. This is the local group, our galactic neighborhood, spanning roughly 10 million light-years across. The local group is dominated by two giants, the Milky Way and Andromeda. These two spiral galaxies contain most of the group's visible mass. Everything else is smaller, often dramatically so. Dwarf galaxies make up the majority of the local group's members, tiny systems containing just millions or billions of stars. The third largest member is the Triangulum galaxy, another spiral roughly 60 billion stars in size. It orbits on the outskirts of the local group, possibly bound to Andromeda gravitationally. Its fate is tied to the approaching merger. It will either collide with Andromeda before the Milky Way collision or join the chaos afterward. Most local group galaxies are invisible to the naked eye. Only Andromeda and the two Magellanic Clouds can be seen without telescopes, and those only from dark sites far from city lights. The rest are too small and too distant to perceive without optical aid. They're ghosts in the cosmic darkness. These dwarf galaxies come in different types. Dwarf spheroidals are diffuse clouds of old stars, barely held together by gravity. Dwarf irregulars contain younger stellar populations and active star formation. Some dwarfs are so faint they're called ultra-faint dwarfs, containing only thousands of stars total. They're barely more substantial than globular clusters. Why do dwarf galaxies exist at all? They're leftovers from the early universe, small systems that formed when the cosmos was young. Many have been disrupted or consumed by larger galaxies over billions of years. The survivors occupy the outskirts of the local group, far from the gravitational violence near the major galaxies. The Magellanic Clouds are the Milky Way's most prominent satellites. Visible from the southern hemisphere, these irregular galaxies orbit our galaxy at distances of roughly 160,000 and 200,000 light-years. They're close enough that tidal forces are beginning to strip stars from their outer regions. The Magellanic Clouds won't survive independently forever. Gravitational interactions with the Milky Way will eventually tear them apart. Their stars will be absorbed into our galactic halo, adding to the scattered stellar population that surrounds the main disk. This process is already underway. Streams of stars stretch between the clouds and the Milky Way, marking the path of disruption. Other dwarf galaxies orbit the Milky Way too. The Sagittarius Dwarf Elliptical Galaxy is currently passing through our galactic disk. Its stars are being stripped away with each passage. Within a few more orbits, it will cease to exist as an independent structure. The Milky Way will have consumed another victim. This consumption is normal. Large galaxies grow by eating smaller ones. The Milky Way has merged with dozens of dwarf galaxies throughout its history. Each merger added mass and stars. Chemical signatures in our galaxy's halo preserve evidence of ancient collisions, ghost structures that reveal our violent past. The local group itself is moving. All 30 galaxies share a common motion through space, falling toward a massive concentration of galaxies called the Virgo cluster. This cluster sits roughly 50 million light-years away and contains over 1,000 galaxies. Its gravitational pull affects everything in the local group. Beyond Virgo lies an even larger structure, the Laniakea supercluster. This is a gravitationally bound collection of galaxy clusters spanning 500 million light-years. The local group is a tiny component of this vast assembly, a minor suburb in a cosmic metropolis. From this perspective, even entire galaxies become insignificant. The Milky Way is just one member of a small group, which is itself part of a larger cluster, which belongs to an even larger supercluster. The hierarchy of structure continues upward until you reach the largest known formations in the universe. But we're not done scaling up yet. Zoom out far enough and galaxies blur together. Individual stars vanish entirely. Even spiral arms disappear. What remains are clouds of light, each cloud representing billions of stars compressed into a single pixel. This is the scale of superclusters, and the Milky Way sits inside one called the Virgo supercluster. The Virgo supercluster spans roughly 110 million light-years. It contains roughly 100 galaxy groups and clusters, including our local group. The total mass exceeds 10,000 trillion solar masses, most of it dark matter. The number of galaxies ranges into the tens of thousands. At the supercluster's heart sits the Virgo cluster, a dense concentration of over 1,000 galaxies packed into a region just 15 million light-years across. This cluster dominates the supercluster gravitationally. Everything else, including the local group, falls slowly toward Virgo's center. The journey takes billions of years. The local group currently sits roughly 65 million light-years from the Virgo cluster's core. We're moving toward it at roughly 1,000 kilometers per second. At this speed, we'll reach Virgo in roughly 20 billion years, long after the Milky Way-Andromeda merger completes. But even the Virgo supercluster is not the largest structure containing us. Recent mapping has revealed that Virgo itself is just one lobe of a much larger formation called Laniakea. This supercluster of superclusters spans 520 million light-years and contains roughly 100,000 large galaxies. The name Laniakea comes from Hawaiian words meaning immense heaven. It's an appropriate name for a structure so vast that light takes 500 million years to cross it. Everything within Laniakea shares a common motion, falling toward a gravitational center called the Great Attractor. The Great Attractor itself is mysterious. It's a region of space containing an enormous mass concentration that pulls on everything around it. The exact nature of this mass remains unclear because it's hidden behind the Milky Way's galactic plane. Dust in our disk blocks our view of whatever lies in that direction, but its gravitational influence is undeniable. Beyond Laniakea, structures become even larger but less well-defined. Galaxy filaments stretch across hundreds of millions of light-years, chains of superclusters connected by tendrils of galaxies. Between these filaments lie cosmic voids, enormous empty regions containing almost no galaxies at all. The largest known structure in the universe is a galactic filament roughly 10 billion light-years long. It contains billions of galaxies arranged in a chain-like structure. Light takes longer to cross this filament than the universe's current age. You couldn't see from one end to the other, even if nothing blocked your view. At these scales, the universe looks like a cosmic web. Filaments and sheets of galaxies surround vast voids. The pattern resembles soap bubbles or foam, with galaxies concentrated on the bubble surfaces and emptiness filling the bubble interiors. This structure arose from quantum fluctuations in the early universe, tiny density variations that grew over billions of years. The Milky Way occupies a relatively typical location within this cosmic web. We sit on a filament, not in a void. We're part of a supercluster, not isolated in intergalactic space. Our position is unremarkable on the largest scales. We're embedded in structure, surrounded by galaxies, typical in every way. From this cosmic perspective, Earth is beyond invisible. Our star is beyond invisible. Even our entire galaxy is just one tiny point of light among countless others. You could delete the Milky Way from existence, and the large-scale structure wouldn't change noticeably. We are statistically meaningless. But even understanding these scales doesn't fully convey how small we are. The time lag makes it worse. Right now, light is leaving Earth, photons bouncing off your skin, reflecting from buildings, radiating from city lights. These photons scatter into space in all directions. Some head toward the galactic center. They begin a journey that will last 26,000 years. What will those photons show when they finally arrive? Earth as it exists today, the year 2025. Human civilization at its current stage of development. Cities glowing with artificial light, satellites orbiting overhead, radio signals broadcasting into space. This is the snapshot traveling toward the core. But by the time these photons reach their destination, Earth will have changed beyond recognition. 26,000 years is longer than all recorded human history. It's 10 times longer than human civilization has existed. Whatever happens to Earth in the next 26 millennia, those photons will show none of it. They're frozen in time, carrying outdated information. Now reverse the perspective. The light reaching Earth from the galactic core left 26,000 years ago. It shows the core as it existed during the last ice age on Earth. Humans were hunter-gatherers. Mammoths still roamed. No cities existed. No agriculture. No writing. The core has changed since then, but we can't see those changes yet. This time lag applies to everything we observe in the galaxy. The stars you see at night don't exist in those configurations anymore. They've moved. Some have exploded. New stars have been born that we can't see yet because their light hasn't reached us. The night sky is a historical document showing the past, never the present. A supernova could detonate at the galactic center right now. The explosion would be catastrophic, releasing more energy in seconds than our star emits in its lifetime. But we wouldn't know for 26,000 years. The light, the radiation, the gravitational waves, all would race toward us at light speed, arriving 26 millennia from now. Communication across these distances becomes absurd. Imagine trying to coordinate with someone at the galactic center. You send a message. It takes 26,000 years to arrive. They reply immediately. Their response takes another 26,000 years to reach you. A simple back-and-forth exchange requires 52,000 years. By the time you receive their reply, you're not even the same species anymore. Humans evolve on timescales of tens or hundreds of thousands of years. 52,000 years is long enough for significant evolutionary changes. The person who sent the original message and the person who receives the reply might not be able to interbreed. They'd be different species. This is why faster-than-light communication appears in science fiction. Without it, coordinating anything across galactic distances is impossible. Real physics offers no loopholes. Information cannot travel faster than light. The time lag is fundamental, built into the fabric of space-time itself. The time lag also means we're seeing the galaxy's history, not its present. Different parts of what we observe exist at different times. Nearby stars show recent history, just years or decades old. Distant stars show older history, centuries or millennia old. The galactic center shows ancient history, 26,000 years past. Astronomers account for this when studying galactic structure. They don't assume everything they see exists simultaneously. They reconstruct the galaxy's present configuration from historical data, calculating where objects have moved since their light left them. It's like archaeology, but for the cosmos. The time lag affects our understanding of galactic dynamics too. We can't observe events happening in real time. We can't watch collisions as they occur. Everything we see already happened. We're studying ghosts, echoes of events long finished. The galaxy we think we know is actually the galaxy that was. And this is just within our own galaxy. Looking at other galaxies introduces even longer time lags. Andromeda's light takes 2.5 million years to reach us. We see it as it existed before humans evolved. The collision we predict is based on ancient data. Andromeda might have already changed course, but we won't know for millions of years. Time and space become inseparable at cosmic scales. Distance equals duration. The farther you look, the farther back you see. Astronomy is time travel, but only backward. We see the past, never the present, and definitely never the future. The galactic center is beautiful in photographs. Bright clusters of ancient stars, glowing gas clouds, the supermassive black hole lurking invisibly at the heart of it all. But it's also lethal. Nothing resembling Earth's biosphere could survive there. The environment is too violent, too hostile, too fundamentally incompatible with complex life. Start with radiation. The core emits X-rays and gamma rays continuously. These high-energy photons come from multiple sources: the black hole consuming gas, neutron stars colliding, supernovae detonating. The radiation level exceeds our neighborhoods by factors of thousands. Any planet's atmosphere would be stripped away by this bombardment. Even without an atmosphere, surface radiation would sterilize any world. DNA breaks down under high-energy radiation. Complex molecules fragment. Life as we know it requires stable chemistry, and stable chemistry requires protection from radiation. The core offers no protection. Stellar density increases the danger. Stars near the core pass close enough to disturb each other's planetary systems gravitationally. A passing star could eject planets from their orbits or send them crashing into their parent star. Stable orbits, the kind Earth enjoys, are rare to impossible in such crowded conditions. The supermassive black hole adds another layer of danger. Anything venturing too close experiences extreme tidal forces. These forces stretch objects along the direction toward the black hole while compressing them perpendicular to that direction. The effect, called spaghettification, would tear apart any planet, spacecraft, or unlucky astronaut. Even at safer distances, the black hole's gravitational influence distorts space-time severely. Time itself runs slower near the black hole compared to distant regions. An observer near the core would age more slowly than someone in the galactic suburbs. This time, dilation is real, measurable, and strange. Supernova rates peak near the core. More stars mean more massive stars. More massive stars mean more supernovae. Each supernova releases a burst of radiation lethal for hundreds of light years. Near the core, these events happen frequently enough that no location remains safe for long. Life needs stability. The core offers only chaos. The magnetic field near the core is also extreme. The black hole's rotation, combined with infalling gas, generates powerful magnetic fields that accelerate particles to near light speeds. These particles form jets that shoot outward from the black hole's poles, though our black hole's jets are currently weak compared to those in more active galaxies. Gas clouds near the core move at extreme velocities. They collide frequently, creating shockwaves that heat gas to millions of degrees. Star formation proceeds violently and erratically. The environment resembles a war zone more than the gentle spiral arms where Earth resides. Even communication would be nearly impossible near the core. The high radiation environment would disrupt radio signals. The dense stellar population would scatter signals. Line-of-sight communication would be blocked by gas clouds and stellar atmospheres. Any civilization attempting to survive there would be isolated from the wider galaxy. Temperature extremes add another challenge. Gas near the black hole heats to billions of degrees. Farther out, temperatures vary wildly depending on proximity to stars and hot gas clouds. Finding a temperate zone suitable for liquid water would be extraordinarily difficult. Gravitational waves ripple through the core constantly. Binary black holes orbiting each other emit these waves as they spiral inward. Neutron star mergers create brief but intense gravitational wave bursts. These distortions in space-time might affect delicate instruments or even biological processes. We don't know. Nobody's been there to check. The core is a fascinating place to study. It teaches us about black hole physics, stellar dynamics, and extreme environments. But it's not a place to visit. It's definitely not a place to live. The galactic suburbs offer safety. The core offers only death. Our distance from this forbidden zone is another aspect of our cosmic luck. Everything in your body was forged inside stars that exploded billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon forming your DNA. All of it was manufactured in stellar furnaces and scattered across space by supernovae. Stars are element factories. They fuse hydrogen into helium, releasing energy that makes them shine. Larger stars continue the process, fusing helium into carbon, carbon into oxygen, oxygen into silicon, and so on up the periodic table. The fusion stops at iron. Creating heavier elements requires energy input rather than releasing it. When massive stars explode as supernovae, the explosion provides that energy. In those brief moments of catastrophic collapse, elements heavier than iron are forged. Gold, silver, platinum, uranium, all created in supernova fireballs. The explosion scatters these newly formed elements into space, seeding the interstellar medium with heavy elements. Early in the universe's history, only hydrogen and helium existed. These elements formed in the Big Bang. The first stars were made purely from this primordial gas. When they exploded, they released the first heavy elements into space. Second-generation stars formed from gas, slightly enriched with these elements. This process has repeated for over 13 billion years. Each generation of stars adds more heavy elements to the galaxy's inventory. Our star is a late-generation star, formed from gas enriched by countless previous stellar cycles. The heavy elements in our bodies have passed through multiple stars, recycled repeatedly over billions of years. The atoms in your body are ancient. They're older than Earth, older than the solar system, older than many stars currently visible in the sky. These atoms have traveled across the galaxy, drifting in molecular clouds, incorporating into earlier planetary systems, being expelled by stellar winds, floating through space again. Some atoms in your body might have originated near the galactic core. Others might have formed in the outer regions. They've been mixed and redistributed by galactic rotation, stellar motions, and supernova shockwaves. Your body is a collection of atoms from across the galaxy's history. This makes you literally connected to the galaxy. You're not separate from it. You're made of it. The distinction between you and the galaxy is artificial. You're a temporary arrangement of galactic material, briefly organized into a thinking structure before returning to the cosmic recycling system. When you die, your atoms don't disappear. They return to the environment. They get incorporated into soil, water, air. Some might eventually escape Earth's gravity and drift into space. Over billions of years, they might be swept up by passing gas clouds and incorporated into new stars. Your atoms might witness the galaxy's distant future. This perspective changes how you think about significance. Yes, you're incredibly small compared to the galaxy, but you're also incredibly complex. The galaxy is mostly empty space punctuated by simple structures like stars. You are an intricate arrangement of particles that can think, feel, and understand the cosmos. The galaxy has produced few things as complex as you. Life itself might be rare. We don't know yet. We've found no evidence of life beyond Earth. If life is common, then perhaps complexity is common too. But if life is rare, then you represent something genuinely unusual, matter that has organized itself into a form capable of contemplating its own origins. The elements in your body traveled through space for eons before arriving on Earth. They witnessed the galaxy from countless perspectives. They existed in stars, in nebulae, in comets, in asteroids. Now they're in you, enabling you to look up at the night sky and wonder about the journey they took. This is the ultimate perspective shift. You're not outside the galaxy looking in. You're not separate from the cosmos. You are the cosmos, examining itself. You are the Milky Way becoming conscious of itself, however briefly. And that brings us to the final truth. Here's the paradox that should break your mind. You are absurdly, impossibly, incomprehensibly small. A biological organism on a planet that's barely larger than a dust mote, orbiting a star that's one among hundreds of billions, located in a galaxy that's one among trillions. You could be removed from existence right now, and the universe wouldn't notice. No cosmic balance would shift. No laws of physics would change. Nothing would care. And yet, despite this crushing insignificance, you possess something the universe itself lacks: consciousness. The ability to understand, the capacity to measure, calculate, and comprehend structures vastly larger than yourself. The galaxy is immense, but unaware. You are tiny, but aware. This makes you more remarkable than any galaxy. The galaxy cannot contemplate its own size. The supermassive black hole at the core cannot ponder the mathematics of general relativity. The spiral arms cannot wonder about their formation. But you can. You can look at the vastness of space and understand it. You can calculate distances. You can grasp scales that dwarf you by trillions. The universe has produced very few things capable of understanding itself. You are one of them. This awareness is bizarre. You're a pattern of atoms, temporarily organized into a thinking structure. The atoms themselves are ancient, billions of years old, recycled through countless stars. But the pattern they currently form, you, is unique. You will exist for decades, maybe a century. Then the pattern will dissolve. The atoms will scatter and reorganize into something else. But during your brief existence, you can understand infinity. You can conceptualize distances measured in billions of light years. You can grasp timescales extending billions of years into the past and future. You can comprehend the existence of hundreds of billions of galaxies, each containing hundreds of billions of stars. The fact that you're small doesn't prevent you from understanding the large. This is the strangest thing about consciousness. It's scale independent. Your physical size is irrelevant to your cognitive capacity. You can think about things vastly larger or vastly smaller than yourself. You can visualize atoms. You can visualize superclusters. Your mind operates outside the constraints of physical scale. Humans have only understood our true cosmic position for roughly a century. Before that, we thought we were at the center of everything. We thought the galaxy was the entire universe. We thought stars were tiny lights embedded in a celestial sphere. Every assumption was wrong, but now we know. We've mapped our location, measured our insignificance, and accepted our position as cosmic specks. This knowledge should be depressing. It should make everything feel meaningless. What's the point of human civilization if we're this small? What's the point of individual lives if the galaxy wouldn't notice our disappearance? What's the point of caring about anything when the scales are this extreme? But here's the answer. The point is that we can ask the question. The galaxy can't ask what the point is. Stars can't wonder about meaning. Black holes can't contemplate existence. But you can. That ability, that consciousness, that awareness, it's the most interesting thing happening in this entire corner of the cosmos. We might be alone. Life might be rare. Consciousness might be rarer still. If that's true, then you're not just small, you're also precious. You're one of the few points in space where the universe has become aware of itself. You're a window through which the cosmos views its own structure. You matter because matter has organized itself into a form that can understand mattering. Or maybe we're not alone. Maybe millions of civilizations exist across the galaxy. Maybe consciousness is common. Maybe the universe is teeming with minds contemplating their own insignificance. If that's true, then you're still remarkable. You're still a thinking pattern, still capable of understanding infinity despite your size. The Milky Way is 100,000 light years across. You are perhaps 6 feet tall. The ratio is incomprehensible. You are smaller than a single atom compared to the galaxy. But you can understand that ratio. You can calculate it, visualize it, and grasp its implications. The galaxy cannot. This is the ultimate perspective. You're infinitesimally small. You're completely insignificant. The galaxy wouldn't notice if Earth vanished tomorrow, and yet you can comprehend the galaxy. You can understand your own insignificance. That understanding makes you significant in a way size never could. So yes, you're small inside the Milky Way, smaller than you can truly grasp. But size isn't everything. Understanding is something. Consciousness is something. Awareness is something. You possess all three. The galaxy possesses none. In that sense, you're not small at all. You're the most complex thing the galaxy has ever produced. The most aware structure it's ever assembled. The first thing it's made that can actually understand what it is. The Milky Way is vast, but you are conscious. And consciousness, however brief and however small, is the only thing that gives the vastness meaning. Without you, without minds like yours, the galaxy would simply exist. It wouldn't matter. It wouldn't mean anything. You're the part that matters. Never forget that.